Most amateur prospectors overlook the way a stone interacts with ordinary glass, not realizing that a real diamond doesn't just scratch it, but cuts into it with a tactile resistance and a nearly soundless precision. It's not the scratch itself that tells the story. It's the edge behavior, the friction, and the absence of powder left behind. To understand why this matters, consider the basic Mohs scale of hardness. Quartz sits at 7, topaz at 8, and diamond far above at 10. But this scale is ordinal, not linear, meaning the difference between 9 and 10 is far greater than between 7 and 8. Quartz, for example, can scratch glass, typically around 5.5, leaving a powdery white trail and a faint squeak. Many mistake this for proof of a diamond. But a true diamond doesn't just mark the glass, it engraves it. The groove left behind is sharper, deeper, and clean-edged, often catching the fingernail. If the stone leaves behind any chalky residue, it isn't diamond. This initial field test, though crude, is deceptively useful when used sparingly and with clear expectations. A controlled scratch on the corner of an old bottle or non-coated window pane is preferable. Hold the stone in a firm grip using tweezers or gloves if needed, and apply moderate pressure at a 45-degree angle. Real diamond will not wear down or show damage from the contact. Simulants like cubic zirconia or high-lead glass may show slight abrasion or lose edge sharpness after repeated attempts. But even more telling is what precedes the scratch. A real diamond in its rough form often exhibits an oily, almost greasy luster that differs from quartz's vitreous shine. Its crystal form may suggest octahedral symmetry, flat triangular faces, and sharp intersections, while quartz typically grows in six-sided prisms with blunt terminations. Under certain angles, a diamond's adamantine brilliance appears metallic and reflective, whereas quartz is more muted, almost frosty. These initial cues should never stand alone. A scratch that seems deep without comparative controls is meaningless in isolation. That's why experienced field collectors always ask, what else is present in the matrix? Are there other hard minerals nearby that might offer context, say garnet or chromite? And did the stone come from a terrain type known to host primary diamond deposits? Because as clear as the scratch might seem, what comes next could overturn everything. How do we separate a real diamond from a synthetic mimic? One that passes the glass test, the luster check, and even shows cubic habit. A synthetic moissanite can pass the glass scratch test just as convincingly as a diamond. And that's where many hopeful finds go sideways. Its hardness, around 9.25 on the Mohs scale, is high enough to leave deep marks, often indistinguishable from those made by real diamond to the untrained eye. But moissanite has tells that diamond never does, and those subtleties begin with light. When you hold a rough or cut stone up to strong illumination, daylight or a flashlight, moissanite reveals a signature trait, double refraction. Through a loop, edges of back facets appear doubled or blurred, almost vibrating. Diamond, by contrast, is singly refractive. This difference, though invisible to the naked eye, is pronounced under 10x magnification. It's one of the fastest ways to eliminate moissanite in a prepared setting, though rough stones demand more scrutiny. In raw form, the confusion between moissanite and diamond arises mainly because both can exhibit greasy luster, are often colorless or near colorless, and resist scratching. But moissanite, being lab-grown in nearly all field cases, often carries surface anomalies. Minute flow lines, unnatural pit clusters, or even edge softness not typical of natural diamond. These may only become evident under microscopy, but in field, there's a faster way. Electrical conductivity testing. While diamonds are superb thermal conductors, they do not conduct electricity. Moissanite, however, does. That's where dual-mode testers come in. Handheld diamond testers based on thermal conductivity, the most common field tool, will beep for both moissanite and diamond. But only dual testers that include an electrical probe can tell them apart instantly. When testing a suspect stone, one probe tip measures heat dissipation, diamond passes. Then the second test applies a light electrical current. If it conducts, it's moissanite. If not, the case for diamond strengthens. Visual clues also offer subtle differences. Moissanite often exhibits a slightly greenish or yellow overtone under sunlight, particularly in stones over 0.5 carats. Diamond tends toward blue fluorescence under long-wave UV light, a feature we'll explore later, though not always reliable as proof. Critically, none of these observations mean moissanite is worthless. It's a valuable simulant in its own right and traded globally. But it does mean that anyone assuming a scratch test equals authenticity is likely to be misled. True diamond confirmation always requires multiple converging indicators. No single test is sufficient. So if we've ruled out moissanite and glass, what should we be looking for next in the field before investing in conductivity tools or optical inspection? The answer lies not in the stone itself, but in the company it keeps. That's where indicator minerals come in, and they often show up first. Long before a diamond ever reveals itself, the ground whispers clues through a suite of other minerals, often far more visible and just as telling. Most field collectors scan gravel bars and creek bends for sparkle or sharp edges, not realizing that the Rayol Trail begins with what surrounds a diamond, not the stone itself. Among the most reliable companions to diamondiferous zones are pyrope garnet, chromite, ilmenite, and magnetite, collectively known as indicator minerals. These form deep within the Earth's mantle and travel upward in the same explosive volcanic events that bring diamonds to the surface, typically through kimberlite or lamprite pipes. When these host rocks erode, the dense minerals concentrate together in stream deposits, beach gravels, or glacial tills, providing a roadmap upstream to the source. In the field, pyrope garnet stands out for its rich red to purplish hue, often translucent with a high luster. Under a hand lens, it's unmistakable, rounded, yet with occasional dodecahedral faces preserved. Chromite appears jet black, often in grainy or sub-rounded forms, and tends to clump with heavier concentrates. Ilmenite, similar in color but with a more metallic sheen, is slightly magnetic, a property that becomes crucial in quick sorting operations using even a basic rare earth magnet. The magnet test, though crude, begins the separation process. Sweep a neodymium magnet through a pan of concentrates. Magnetite will leap instantly, while ilmenite may shift slightly. The non-magnetic residue, if still dark and dense, could include chromite or garnet. These aren't just geological curiosities. They are direct signals of mantle-derived pipes upstream. However, habit matters. A single garnet in a pan means little without context, but a cluster of garnet, chromite, and ilmenite together, especially when grain sizes exceed 0.5 millimeters, warrants serious attention. The likelihood of kimberlite origin rises sharply with the presence of multiple indicators, particularly if they appear in a downstream orientation relative to known craton margins or faulted terrain. Crucially, diamonds themselves are rarely found in the first pass. Their small size, lack of color, and often rough surfaces make them easy to overlook in favor of glitzier minerals. But the density range of these indicators, garnet 3.8, chromite for 0.5, ilmenite for 0.7, closely mirrors that of diamond, 3.52, allowing for joint concentration using sluices, pans, or sieves. What separates the expert from the enthusiast isn't just the ability to spot a shiny stone. It's the recognition that a handful of black grains in a stream bed may signal a multi-million-dollar source hidden upstream. So how does one begin collecting these indicators methodically? And what tools are essential to separate signal from noise in the field? Most people begin with a shovel and a dream, but without a method to isolate indicator minerals, the odds of success plummet. The terrain itself holds the first answer. Diamond-bearing rocks rarely weather in flat valleys or open plains. They erode from high-pressure volcanic conduits exposed along faults, ancient cratonic margins, or uplifted terrains where erosion can release mantle materials into the sediment chain. So the first tactical move is terrain reading. Look for meander cut banks, inside bends of streams, or coarse gravel bars downstream of steep slopes. These spots slow water enough to drop heavy material, including garnet, chromite, and possibly diamond, into discrete pay layers. In older river systems, paleochannels now dry or diverted often preserve concentrated layers missed by surface scanning. Field collection starts with gridding. Divide your chosen zone into 10 by 10 meter squares or smaller, depending on terrain complexity. Using a standard screen stack, often number 20, 0.85 millimeters, and number 40, 0.425 millimeters, sift 10 to 15 liters of gravel per grid unit. The upper screen removes organics and oversized clasts. The lower isolates fine heavies. Wash gently in a pan or sluice. A bâti pan, with its large surface area and fine control, is preferred for separating the dense sweet from surrounding material. Once the concentrate is reduced, the eye takes over, but with help. A basic magnet sweep through the drying concentrate will remove magnetite and tease out ilmenite. Note that while ilmenite is only weakly magnetic, its behavior under a strong neodymium magnet in short pulses, drag, tap, release, can give it away. The remaining concentrate, often a mix of black, red, and brown grains, should be dried, labeled, and stored per grid square for later microscopic examination or hand lens sorting. Key features to note: garnets with high luster and purplish tint, chromite with blocky angular grains, ilmenite with a metallic blue-black sheen. If these appear in significant quantity in multiple grids, the upstream terrain should be prioritized for follow-up. This is especially critical if terrain maps suggest proximity to peridotite-rich pipes, old lamproite flows, or deeply weathered blue-ground kimberlite. Many prospectors miss the clue density in these concentrates. A single grid square may yield 30 to 50 garnets per 10 liters of gravel. That density, if sustained across a drainage, strongly suggests a nearby source. Conversely, scattered or isolated finds often indicate long transport, diluting the discovery value. But before excitement overtakes caution, one major complication looms. Several of these indicators, particularly garnet and chromite, occur in non-diamond contexts too. That's where the next tier of testing and disappointment often begins. Few setbacks sting more than hauling back kilos of promising concentrate. Deep red garnets, dense black grains, strong magnetic pull, only to discover the indicators aren't what they seemed. In the world of diamond exploration, false positives are not just common, they're routine. And unless you learn to distinguish diagnostic minerals from their mimics, you'll spend time and resources chasing phantoms. Pyrogarnets are the prime example. These deep red, glassy grains are often celebrated as diamond pathfinders. But not all garnets are created equal. The critical subtype linked to diamondiferous pipes is CR pyrope, a chromium-rich variety that typically exhibits a purplish hue and very specific chemical behavior. Unfortunately, grossular, almandine, and even spessartine garnets can mimic pyrope in field conditions. Without microprobe analysis or colorimetric field tests, like chelating paper strips that react to CR3+, there's no instant confirmation. Chromite presents a similar problem. The true diamond pathfinder is MG-rich and often sourced from ultramafic rocks in kimberlite. But other black, opaque minerals such as magnetite, titanomagnetite, or even weathered spinels can look nearly identical under low magnification. The only consistent in-field separator is a magnet test. Magnetite responds strongly, while chromite usually doesn't. But when ilmenite enters the mix, which is only weakly magnetic, things get muddy fast. Even ilmenite, a useful indicator, suffers from duplication. Many weathered basalts and mafic intrusions produce ilmenite-like grains that have no connection to diamonds whatsoever. And to make matters worse, secondary environments like beach placers or glacial tills may blend genuine indicator grains with thousands of irrelevant lookalikes from unrelated geologies. To navigate this minefield, serious field workers establish indicator suites, not single signals. A lone garnet or chromite grain might be a red herring, but finding pyrope, chromite, and ilmenite together in multiple grid samples in a downstream flow consistent with known pipe-hosting terrain. That's pattern recognition, and it counts. But suppose the mineral suite holds up under field logic. The next risk is misinterpreting host material. Kimberlite and lamproite can weather to confusing matrices, sticky clays, decomposed serpentine, and yellowish gravels that seem unremarkable. Many walk past weathered, yellow ground kimberlite without realizing it's the oxidized cap of a much deeper structure. Others mistake peridotite fragments as worthless. Yet peridotite, with its olive-green olivine grains and coarse ultramafic texture, is often apparent rock in diamond-bearing systems. For every false positive, there's a learning cost. But each misidentification sharpens your mineral literacy. Over time, you develop not just the eye for grain color and luster, but the intuition for pattern, which combinations matter and which ones mislead. Still, a good indicator suite isn't enough to stake a claim or call on buyers. What's needed next is a replicable process, one that produces consistent evidence across time and space. And that means refining the field workflow to remove luck from the equation. Luck finds a stone once. A method finds a source. Without a disciplined, repeatable field workflow, even experienced prospectors risk mistaking isolated indicators for real potential. The difference between a one-time anomaly and a traceable pipeline comes down to process consistency, from sampling to record keeping. It starts at the point of collection. Every field effort must be grid-referenced and sample-controlled. For each location, record GPS coordinates, date, terrain type, sample volume, in liters, sieve mesh used, and water flow conditions. If terrain slope, nearby faults, or host rock exposures are visible, note them. This context transforms raw findings into mappable patterns. Each sample should follow a standard progression: screen, wash, magnet sweep, drying, lens inspection. Use nested sieves, typically number 20, 0.85 millimeters, over number 40, 0.425 millimeters, to isolate heavy finds where indicator minerals tend to collect. Discard organic and light material early and concentrate on mid-sized, sub-rounded grains. After panning, allow the residue to dry on clean, labeled trays. Only then should you conduct magnetic separation. Use a rare earth magnet inside a plastic bag to pass over the dried sample in slow, controlled sweeps. Note both what clings and what resists. Heavy, non-magnetic grains are typically more promising. Garnet, chromite, zircon. Document color, grain count, and apparent luster under hand lens or microscope. Take macro photographs when possible to compare samples normalized by volume. For example, 20 pyro garnets in a 10-liter sample equals 2 garnets per liter. Over multiple grids, this allows pattern tracking. Clustering in 3 or more adjacent grids points to directional flow or proximity to source. Grids should follow the terrain, particularly upstream of high indicator hits. Establish grid lines along likely paleochannels, cut banks, and gravity drop zones, locations where water would have historically slowed enough to allow dense material to settle. Between samples, measure slope angles and evaluate exposure. Weathered kimberlite is often clay-rich and yellowish, oxidized, while fresher blue ground occurs deeper and may require coring or shallow trenching. Recording negative samples is just as important. Absence of indicators in a zone helps constrain boundaries and models flow paths. Map these with red X's to identify where to stop sampling just as much as where to continue. This grid and concentrate model isn't just about being methodical. It builds repeatability. Other collectors, geologists, or institutions can test your findings, verify mineral types, and reconstruct indicator paths. And when it's time to talk to labs or investors, this documentation shifts your discovery from a hunch to a pre-validated prospect. Yet, even with a solid indicator pattern and field consistency, there's one more barrier: distinguishing true positives from brilliant imposters. Because a flawless, gem-clear grain might pass every initial test and still be wrong. It's a painful irony. The clearer and more perfect the rough stone appears, the higher the chance it's not what it seems. In the field, several glassy, hard minerals can pass the scratch test, mimic diamond luster, and even resemble octahedral form. That's where secondary tools, UV fluorescence, thermal conductivity, and specific gravity become essential. Each offers partial truth. None are definitive alone. But together, they frame a picture that field eyes alone can't complete. Start with UV. Under long-wave ultraviolet light, 365 nanometers, many natural diamonds emit a blue fluorescence, sometimes strong, sometimes faint. That glow can help flag real stones, especially against inert quartz or weakly fluorescent simulants. But fluorescence is not a guarantee. Some diamonds don't fluoresce at all, and some synthetic or treated stones emit deceptive colors. Worse, certain highly glasses and moissanite can fluoresce too, usually in yellowish or greenish hues. So while UV helps filter the pool, it should be read as a bonus indicator, not a verdict. Next is thermal conductivity. Diamond is among the best thermal conductors known, far outperforming quartz, glass, and zircon. Handheld testers exploit this by measuring how quickly a stone dissipates heat. Touch the probe to a suspect crystal. If the needle or sound indicator responds instantly, the stone is conducting heat well. That's promising. But moissanite also conducts heat well enough to trigger false positives on basic testers. That's why advanced field testers often come with dual probes, one for thermal, one for electrical conductivity. Diamonds don't conduct electricity, moissanite does. The combination of the two readings helps cut through ambiguity. Then there's specific gravity, an often overlooked but powerful test, especially in field labs or at camp. Diamonds have a specific gravity of 3.52. Quartz is significantly lighter, 2.65, while most high-lead glass ranges between 2.4 to 3.0. Moissanite and topaz both hover near 3.6. The margin is thin but measurable. A simple field rig using a digital scale, water displacement container, and suspension wire can determine SG within plus or minus 0.05. To test, weigh the stone dry, then suspend it in water. The formula is SG equals dry weight / dry weight submerged weight. While this test takes longer and requires care, no air bubbles, stable water temp, it eliminates much guesswork when applied consistently. A stone that scratches glass, shows greasy luster, fluoresces blue, conducts heat but not electricity, and lands at 3.52 SG is a near-certain diamond candidate. Still, even with converging results, remember, lab confirmation is the final authority. But field testing allows you to triage, to decide what's worth keeping, what to ditch, and what to escalate. That's how experienced prospectors minimize cost while maximizing accuracy. Once the tests isolate a true candidate, attention shifts back to the environment, because even a confirmed diamond is just a grain until you can trace it back to its geological origin. A single diamond in a pan is a triumph, but it's not a source. To reach the origin, you need to read the land itself. Most diamond finds begin in secondary deposits, streams, gravel beds, beaches, where water, ice, or gravity has transported and concentrated material far from its volcanic birthplace. But the real value, the repeatability, lies in locating the primary host rock, where diamonds form and reside before erosion. Understanding the terrain logic is what turns a loose stone into a pipeline. Primary diamond deposits exist almost exclusively within ancient, stable parts of Earth's crust called cratons. These regions, billions of years old, act as delivery platforms for deep mantle material forced upward by rare volcanic events. The two major rock types associated with diamonds are kimberlite and lamproite, both ultramafic, volatile rich pipes that punch explosively to the surface from depths over 150 kilometers. Mapping their remnants requires knowing what to look for. Fresh kimberlite is often bluish-green and clay-rich, nicknamed blue ground. It weathers to a crumbly yellow-brown material known as yellow ground. These oxidized zones can look like nothing more than discolored soil unless you dig. Lamproite, rarer but just as important, has more variable textures, bubbly, vesicular flows, or brecciated masses with glassy pockets and weathered olivine. These pipes are not always obvious at the surface. In many regions, especially Canada, Australia, and India, they're buried beneath glacial tills or later sediments. But their erosion patterns leave clues. Streams draining kimberlite terrain often carry garnet, ilmenite, and chromite in downcutting channels. Nearby hillsides may show clusters of serpentine boulders or altered ultramafic float, both of which signal pipe country. Uplifted terrain near fault intersections is especially promising. Volcanic conduits often exploit crustal weaknesses to ascend. In secondary deposits, particularly alluvial systems, diamonds tend to concentrate in trap sites, inside bends, bedrock cracks, plunge pools, and behind obstructions where water velocity drops. Over time, these zones act like natural sluices, isolating heavies, garnet, gold, and diamond included. But these locations only receive diamonds, they don't generate them. So when a stone turns up, the clock starts ticking. How far could it have traveled, and what terrain lies upstream? Transport distance depends on multiple factors: topography, climate history, sediment load, and human interference. In tropical zones, diamonds can move kilometers. In glacial regions, they may be dragged hundreds of kilometers from their source. But in steep, confined catchments, diamonds may not move far at all. That's why mapping catchment basins, comparing indicator densities across grid lines, and noting elevation changes are vital. The goal is convergence, where multiple indicator streams trace back toward a single ridge, exposure, or magnetic anomaly. And here's where things often shift. You may discover that the stream isn't cutting across pipe-bearing rock, but down alongside it, just missing the eroded contact zone. A shift of 10 meters upslope could reveal weathered kimberlite boulders or a brecciated margin, previously hidden beneath brush or tailings. When the land starts answering the lab and the gravel matches the grid, you're no longer prospecting, you're pinning down a system. The reversal came not from a failed test, but from a lab report that said everything was right, except the origin. The diamond was real. Specific gravity, 3.52. Thermal and electrical conductivity, perfect match. Blue fluorescence under long-wave UV. Adamantine luster, no double refraction. But when the stone was submitted for Raman spectroscopy and infrared absorption analysis, the spectral fingerprint showed trace elements inconsistent with the local kimberlite field. The nitrogen aggregation state, indicative of crystal growth environment and age, pointed to an entirely different geological source, one not mapped anywhere nearby. This was not an isolated mistake. Across multiple prospecting zones, diamonds that matched terrain logic in the field began to fail the provenance logic in the lab. The problem wasn't with the stones, it was with the assumption that they had eroded from local pipes. In reality, several had arrived through secondary transport routes, much longer and more complex than surface mapping revealed. The most common culprit, glacial transport. In northern latitudes, Canada, Siberia, northern Europe, ice sheets during the Pleistocene moved diamond-bearing till hundreds of kilometers from their source. A diamond found in Alberta might trace back to a pipe in the Northwest Territories. The till blankets, often tens of meters thick, overlie entirely different bedrock, giving the illusion of local derivation. In other cases, human activity caused the misdirection. In parts of India and West Africa, diamonds once discarded in tailings during early colonial-era mining were unknowingly spread downstream during monsoon floods or roadwork, seeding new gravel beds with out-of-place stones. Even some high-value finds in river gravels were eventually traced to mechanical redistribution, not natural erosion. Then there are the outliers. Alluvial diamonds with type IIA purity, almost nitrogen-free, exceptionally rare, discovered far from any known lamproite or kimberlite pipe. In one case, a South American sample turned out to have African mineral inclusions, suggesting it had arrived via transoceanic shipping centuries earlier and been lost, only to be recovered from a modern drainage. These reversals do more than complicate field strategy. They remind us that diamonds, while geologically anchored, are also historical artifacts, subject to drift, trade, loss, and misplacement. That's why origin analysis now includes not just mineralogy, but isotopic studies, trace element chemistry, and inclusion provenance to triangulate where a diamond truly comes from. For field workers, this introduces a new layer of caution. Even with perfect field indicators, the only way to confirm a local source is to find diamond in situ, within or immediately adjacent to kimberlite or lamproite matrix. Anything else remains circumstantial, however compelling. So if diamonds can fool us even after test confirmation, where can we turn for ground truth? The answer lies not in the stones, but in the repeatability of the mineral suite and how it conforms to documented discovery patterns. Once the dust settles from a provenance shock, serious exploration regains footing by anchoring to standardized practices, those proven across decades of study and thousands of drill samples. These aren't hobbyist guesses or isolated anecdotes. They're frameworks established by national geological surveys, diamond majors, and academic consortia designed to separate signal from noise in a global field riddled with variables. At the core is the concept of indicator mineral dispersion halos. Major studies, especially in Canada's Slave Craton and Russia's Yakutia fields, have mapped how indicator minerals migrate downstream from primary kimberlite sources. These studies show consistent patterns. Chromite and pyrope often travel farther than diamonds due to size and durability, while ilmenite tends to break down sooner. By measuring grain concentration gradients across mapped catchments, geologists can reverse trace flow paths and triangulate hidden pipes. This process isn't theoretical. It's supported by grid sampling at known deposits like the Ekati and Diavik mines, where secondary indicators cluster in narrowing bands pointing directly to source. These models help eliminate false positives by highlighting patterns incompatible with kimberlite dispersion. For example, indicators spreading in all directions or persisting uniformly across a flat basin. The field application of this is straightforward. Once indicator minerals are recovered from at least 5 grid squares, plot them spatially and normalize for sample volume. Overlay this map onto topography and known geological features, faults, dikes, and mapped ultramafic bodies. If the density increases toward an upland zone or coincides with a known magnetic anomaly, often present in kimberlite, the probability of a nearby pipe increases sharply. To test these patterns at scale, recognized institutions recommend a stepwise approach. First, confirm indicator mineral identity via microprobe or SCM, scanning electron microscopy. Then conduct heavy mineral geochemistry to check for chromium content in pyrope, magnesium-iron ratios in ilmenite, and TO2 levels in chromite. These values aren't just academic. They correlate directly with diamond association in globally benchmarked datasets. Institutions like the Geological Survey of Canada and the Russian Academy of Sciences maintain mineral chemistry databases that allow field samples to be compared against known productive signatures. If your garnet suite matches the chemistry of pipes that have historically yielded diamonds, the case strengthens exponentially. Equally important is the chain of custody. Field samples must be bagged, labeled, and tracked with unbroken documentation. Labs require clear provenance to ensure analysis results can be trusted and mapped. This becomes critical when findings transition from exploration to licensing or commercial negotiation. By aligning your fieldwork with these established methods, sample control, grid mapping, mineral verification, and comparative geochemistry, you convert isolated discoveries into systematic exploration. It's not just about what you find, but how you find it, and whether the pattern holds up to scientific scrutiny. Still, even the best protocols are meaningless if applied in the wrong geological context. Not every terrain is diamond-bearing, no matter how convincing the clues. No method, no matter how rigorous, can overcome the wrong geology. That's why one of the most decisive questions in diamond exploration isn't what you found, but where you're looking. Despite thousands of hopeful ventures, Only a fraction of the Earth's crust hosts the conditions necessary for diamonds to form, survive, and be transported. Understanding those regional filters means narrowing your search and avoiding wasted effort. The global distribution of economic diamond deposits follows one primary rule: stable cratonic roots, typically over 2.5 billion years old, are the only regions where diamonds consistently form and remain intact during their journey to the surface. These ancient continental cores are geologically thick and cold, two essential conditions that preserve diamonds deep in the mantle before explosive emplacement. Start with Africa. The Kapval Craton in South Africa and the Congo Craton in Central Africa have produced some of the richest primary diamond pipes on Earth, including the iconic Kimberley and Premier mines. West Africa's Man Shield also hosts alluvial diamond fields, though many are reworked from older, poorly mapped sources. Here, both kimberlite and lamproite intrusions have been documented, but access, erosion, and political conditions complicate fieldwork. In Russia, the Siberian Craton is home to the massive Mir and Eudachnia pipes, deep-rooted kimberlites that erupted through ancient Archean terrain. Their success informed modern exploration strategies worldwide: magnetic surveys, indicator halos, and geochemical mapping. Australia's diamond story hinges on lamproite rather than kimberlite. The Argyle mine in Western Australia produced vast quantities of pink diamonds from a deeply weathered lamproite pipe, intruding Proterozoic sediment. This unique geologic setting, non-cratonic, younger, but favorable, expanded the accepted model and taught the industry not to ignore unusual host rocks, provided other indicators were present. Canada, once considered diamond poor, is now a top producer thanks to discoveries in the Slave Craton, particularly at Akati and Diavik. These emerged from glacial till sampling that revealed strong indicator suites well before diamonds were recovered. Cold climates preserved delicate mineral patterns, enabling reverse tracing to buried pipes beneath lake beds and tundra. By contrast, some regions are persistently misleading. Much of South America lacks the cratonic stability required to host primary deposits, despite widespread alluvial diamonds in Brazil and Venezuela. Many of these are relics, eroded from pipes long vanished or transported overland from Africa via ancient supercontinent breakups. Similarly, India's famous Golconda stones originated in Archean terrain, but most surface sources have long been exhausted or buried under dense sediment. Even within favorable regions, terrain type matters. Diamonds don't survive well in high-temperature metamorphic belts, active volcanic arcs, or young oceanic crust. Field efforts in these areas, no matter how careful, rarely succeed. So before sieving gravel or mapping indicators, consult regional geologic maps. Overlay your intended search area with craton boundaries, known ultramafic intrusions, and previous exploration records. If your site lacks either a kimberlite/lamproite host or documented indicator patterns, it's unlikely to yield meaningful results. Still, terrain knowledge alone doesn't guarantee success. Even in the right place, confirmation hinges on identifying not just diamonds, but the minerals that precede and predict them. Each diamond type has its own diagnostic fingerprint. And next, we'll examine how those types diverge and what they reveal about origin, habit, and market. Not all diamonds are created equal, and the differences matter long before a stone ever reaches a cutter's bench. From the moment a rough diamond is found, its type influences everything: likelihood of origin from a specific host rock, structural clarity, fluorescence response, and eventual market value. Field identification isn't just about is it a diamond, but what kind of diamond is it, and what that implies. The key classification begins with diamond types, based on nitrogen content and structure. There are 4: Type IA, IB, IIA, and IIB. Though field tools can't fully distinguish these, understanding their associations helps guide expectations and follow-up tests. Type IA diamonds, making up over 95% of natural stones, contain nitrogen atoms clustered in aggregates. They often fluoresce blue under UV light and tend to be found in traditional kimberlite-hosted deposits, South Africa, Siberia, and Canada. Their presence in a sample often confirms geological compatibility with classic pipe systems. Type IB diamonds are much rarer, less than 0.1%, containing isolated nitrogen atoms. These often display brownish or yellow hues and are more likely to occur in lamprite-hosted systems, like Australia's Argyle mine. This subtlety matters because a yellow diamond in a region previously dismissed might suggest a lamprite pipe, not a kimberlite one, a discovery with significant implications. Type IIA diamonds are the holy grail. These contain no measurable nitrogen, are often exceptionally clear, and sometimes large. The Kohinoor and other famous historic stones are type IIA. Their natural occurrence is limited but includes Golconda, India, parts of Brazil, and pockets in Africa. These are most likely to form in deep sublithospheric conditions, rare even by diamond standards. In the field, a flawless, colorless stone with no fluorescence and high brilliance under natural light may hint at type IIA origin. Type IIB diamonds are also nitrogen-free, but contain boron, making them semiconductive. They exhibit blue or gray color due to the boron content and are electrically conductive, one of the very few diamond types that will fail the standard electrical non-conductivity test. This rare behavior is a red flag in the field. A stone that passes all diamond indicators but does conduct electricity may not be a false positive. It may be a type IIB. These are extremely rare and command high prices. While these types can't be definitively diagnosed in the field, certain behaviors align predictably. UV response, color, and transparency offer partial signals. A bluish fluorescence under long-wave UV likely indicates type IA. No fluorescence with flawless clarity might suggest type IIA. Yellow or brown overtone could point toward IB or a plastically deformed IA. Electrical conductivity raises the possibility of IIB if moissanite is ruled out. These differences aren't just academic. Buyers, labs, and cutters use diamond type to determine value ceiling, cutting potential, and even legal exportability. Some jurisdictions require specific type testing before high-value stones can be sold internationally, particularly if they might qualify as type IIA or IIB due to their elevated market interest. For field prospectors, these signals help prioritize samples. A cloudy, non-fluorescent, low-luster grain may be authentic, but has limited upside. A clear, octahedral crystal with no UV response, perfect luster, and non-conductive behavior should be flagged for expedited analysis. By focusing not only on the presence of diamonds but the type traits they exhibit, prospectors gain an edge, prioritizing effort and cost towards stones that truly move the needle in the market. But even perfect fieldwork and ideal diamond types can stumble if the wrong assumptions about land access or safety go unchallenged. The promise of a field diamond is only as strong as the ground it came from, and many prospectors learn too late that access is not permission. Even if a stone is legally yours, the land under your boots may not be. Ignoring land rights, safety risks, or environmental hazards doesn't just jeopardize a find. It can void it, or worse, lead to legal action, injury, or claim invalidation. Start with land access laws. In many diamond-producing countries, mineral rights are separate from surface rights. This means even if you have permission from a landowner to explore, that doesn't grant you rights to extract or claim what's below. Some nations, like South Africa and India, vest mineral ownership in the state. In Canada and Australia, certain provinces allow mineral claims to be staked, but only after formal registration and sometimes with indigenous consultation requirements. The first step is always a title search. Use local geological survey databases to check existing claims. Many regions maintain GIS portals showing current exploration licenses, mining permits, and restricted zones. Sampling without checking these is a common and costly mistake. Then there's permit structure. In jurisdictions like Brazil, even basic sampling may require an exploration license. In Russia, unauthorized removal of mineral specimens, even surface float, can carry legal penalties. In West Africa, artisanal mining is permitted under community-based systems, but only in designated zones. Violating these rules risks confiscation of equipment or worse, serious legal action. Beyond legality is safety. Some of the most diamond-rich zones lie in high-risk environments, flood-prone valleys, steep, unstable slopes, or regions with residual chemical tailings from previous operations. Weathered kimberlite can appear firm but collapse underfoot after rain. River gravels may hide sinkholes or be cut off by flash floods within minutes. Always assess slope stability, local weather history, and upstream dam conditions before entering a site. Wildlife also plays a role. In Siberia and Canada, remote areas mean potential encounters with bears or wolves. In tropical regions, snakes, insects, or even aggressive territorial animals are routine hazards. Pack accordingly. Safety kits, bear spray, anti-venom protocols. These are as essential as a hand lens or sieve. In community zones, conservation etiquette must be observed. Digging along riverbanks, especially near villages or communal farmland, can degrade water quality or damage cultural sites. In some regions, unpermitted disturbance of riverbed gravel is treated as environmental damage, even for small-scale efforts. Importantly, even lab-confirmed stones can become legally worthless if their collection violated regulations. Most gemological labs require origin documentation for certification. If a diamond's provenance includes trespassing, permit violations, or undocumented chain of custody, many labs will refuse to grade or register it. That alone can slash value or make the stone unsellable on formal markets. These realities make one principle clear: field ethics are not optional. Before you test, pan, or sample, ask, register, record, protect. Because a verified, legal, and safely recovered diamond carries not just value, but credibility. Once the ground is secure and the sample confirmed, the next logical step is verification. Building a solid grid, repeat testing, and knowing exactly when it's worth investing in formal lab analysis. The most expensive mistake in diamond prospecting isn't missing a stone. It's overcommitting to a false lead. A single promising find can tempt even seasoned field workers to escalate too quickly. Lab tests, land negotiations, gear upgrades. But serious exploration only scales when repeatability proves the anomaly is part of a pattern. That means before any money moves, you need a grid. A verification grid turns raw curiosity into a quantified discovery. Start by mapping the exact location of the original find, then extend outward in concentric radiating squares or a fan-shaped transect if terrain dictates. Standard spacing is 25 to 50 meters per sample point, depending on topography and drainage complexity. Each point should yield the same sample volume, ideally 10 to 20 liters of screen concentrate, and undergo the full process: wash, dry, magnet sweep, indicator tally. The aim isn't just to replicate the diamond. It's to replicate the indicator suite consistently, finding more pyrope, chromite, and ilmenite grains across adjacent grids, especially with increasing density toward an upstream or upslope direction, supports a local source. If indicators vanish after 100 meters or spread randomly without concentration, the original find may be a transported outlier. Document each grid point meticulously: GPS slope, distance from water, sample mass, grain counts per indicator type. Take photos of sample trays, sieving stages, and concentrate under magnification. This log doesn't just reinforce your internal model. It creates a paper trail for labs, potential investors, and government inspectors. The threshold to move from field testing to formal lab analysis usually arrives when 2 or more grid points produce 1. Consistent indicator suites, and 2. A second diamond or confirmed kimberlitic float, fragments of blue ground, serpentinized peridotite, or mantle-derived xenoliths. At that stage, submitting key concentrates to a certified lab makes sense. Labs typically perform SEMEDS, scanning electron microscopy with energy-dispersive X-ray spectroscopy, to confirm mineral identity and composition. A positive CR2O3 reading in pyrope or MgO, Fio ratios and ilmenite consistent with known diamond-bearing pipes greatly strengthens your case. Costs vary, $250, $800 per sample set, depending on scope, but strategic selection reduces waste. Don't send the diamond yet, unless it's over 0.5 carats or gem clear. Early submission rarely yields return on cost. Instead, send the context. Labs value sweet confirmation more than the first gem, which can be isolated or misplaced. Only when a repeat diamond is found in situ, within fresh or weathered matrix, or when 3+ verified indicator grids point to the same origin, should the diamond itself be submitted for spectroscopy, classification, and valuation.